Good evening, students. Today we are going to learn about two important topics of this chapter. One is transformation of energy or the law of conservation of energy. Then the second topic will be our power, also called as rate of doing work. So what is this law of conservation of energy or transformation of energy? That we shall start. Students, we have learned that energy can be in various forms. In that we have learned the two common. One is kinetic, another one is potential. So this energy that we have learned can be in various forms. That we have learned yesterday that this energy may exist in the form of heat or light or mechanical energy. So it can be in various forms. Even kinetic energy is one of the form and potential energy is the other form. So this one form of energy can be converted into the other form, or the other form can be converted into the first form. Like it is possible to convert potential energy into kinetic energy. At the same time, it is also possible to convert the kinetic energy into potential energy. So this conversion is called as transformation. A student, it need not be only potential and kinetic. It can be heat as well as mechanical energy. So heat into mechanical or heat into light energy. So all these things. This mechanical can be your potential energy or kinetic energy. Even the mechanical energy can be converted into heat. Where we are absorbing mechanical energy gets converted into heat. Students, mechanical energy gets converted into heat is absorbed quite frequently. Like if you smash one of your friend on his cheek, what you observe? The cheek become heated or become red. Why is that? Say your father or mother beats you or just snap you, what you observe, that portion get heated. Why? Because whatever the mechanical energy or kinetic energy present in hand, that gets converted into the heat at your cheek or your the body part where it is heating. So this way the mechanical energy gets converted into heat energy. Not only heat, even while heating you are absorbing the sound. Why the sound is produced while one is colliding with the other? It is because the kinetic energy present in the moving body gets converted into the sound energy. So this way, the same thing can happen here. Means the mechanical can be converted into heat or even the sound. So this may be converted into the sound energy. So all these conversions means one into another. Even the sound energy can be converted into the mechanical energy. Like when this is happening, a student, this sound, what I am speaking, is able to push the diaphragm or something present inside this microphone. Though there are various kind of microphones, means that diaphragm then vibrates forward to produce the electrical energy. So this way the sound into mechanical, mechanical into electrical, the electricity that we are observing, that we are getting from the generator because of the rotation of their rotor part. So this way this mechanical means sound even converted into the mechanical, even the mechanical into electrical, where we are observing, you are observing that in your cycle there is a dynamo when it is pushed over your wheel, and then while you are riding the cycle the ball in front of your cycle that starts glowing. The lamp starts glowing. Why? Because of rotation, the dynamo starts rotating. As a result, the magnet is able to convert this mechanical into the electrical. This way the light glows. Similarly, the electrical energy is able to be converted into the mechanical. Where is this? Electrical to mechanical we are observing in our daily life. In fan, while you are switching on the fan starts rotating. Why? The electricity passes through the coil of the fan and the fan starts rotating. So rotation is what? Mechanical energy or kinetic energy. This way one form gets converted into other. So all of these conversion from one form to other form is called transformation. So these are transformation or conversion of one form of energy into other. Means we are observing this frequently, that energy can be converted from one form to another. Then we have to learn about the law of conservation of this energy, which tells that while one energy is converted into another, only their form are changing. So energy is not lost, but energy just get changed into the other form. So that much simple is our law of conservation of energy. So let us go for law of conservation of energy. What is that? So student, we shall be very much careful. Mechanical to electrical, where we are observing in the generator or dynamo. Then electrical to mechanical in motor. This motor is connected in our fan and many more places, even in your fridge and many more places where there is some rotation. So this transformation, so how this transformation of energy can take place? For that there is a law called law of conservation of energy. So what is this law of conservation of energy? A student, this energy could be in any form, maybe your mechanical energy, or maybe electrical energy, or maybe heat energy, or maybe sound energy. Means it can be sound, heat, electrical, maybe your mechanical. Mechanical include your both potential and kinetic. Okay, it is like this one. So what this law of conservation of energy tells that energy can be converted into one form to another, but during conversion there is either no net creation of energy or there is no loss of energy. Like while you are smashing the other, or your parent is just putting a smash over you, then the mechanical energy present in the hand that get converted into the sound. That's why the sound is produced. The heat, that's why the cheek get heated. The other, while stopping, more energy is converted over the skin, that's why it become red. So this law tells that energy can neither be created nor be destroyed, only its form can be changed. So right, this law tells that, or according to law of conservation of energy, energy can neither be created nor be destroyed, Neither be created means no net energy can be generated from somewhere. It is just obtained by conversion of one form of energy into another. So energy can neither be created nor be destroyed, but its form can be changed. Okay, so only this tells that its form can be changed. That is, there is transformation of energy. So this transformation or conversion from one form to another, that is, there could be transformation of energy. But while there is transformation of energy, there will not be any loss or gain of energy. Whatever the energy in one form, that will just get converted into another form. So that's why we can write its form can be changed. That is, there could be transformation of energy. Transformation of energy from one form to another form, or from one type to another type. So only this form change in form is our transformation. Like I had explained earlier, the heat may be converted into the mechanical, where we are observing while you are heating the cooker containing some amount of water and your food item, you are observing that after some time the CT starts blowing. Why? Because the heat is being converted into the steam, and steam is able to lift the whistle or CT of the cooker. Therefore the steam try to come out. So it's heat which is converted into the mechanical energy of the steam, and steam is able to move out. So movement or speed or pressure is the mechanical energy. Okay, student. So it is this one. Example of this conversion. Let us write few. The electrical energy get converted into the rotational energy or mechanical energy in fan. So in fan, what is happening? Fan, or rather motor, we can write more general term, wherever the motor is there. While you are supplying the electrical energy gets converted into which form? The rotation of the blade.
Mechanical.
So that rotation is our mechanical energy. It's very simple, provided you just understand. So mechanical energy, any kind of motion or because of its position. So here it is the rotation. Rotation is also a kind of motion. It is circular motion. Means it is the kinetic energy. Kinetic energy is a mechanical energy. So it is this one. You may take the other. Like in hydel power plant, what is happening? Inside the dam, there is large amount of water stored on one side of dam, though on the other side there is a river which is flowing. What is happening? Wherever there is an opening, these are the waters, this is the dam, it is holding the water to certain height. So it is our dam. On one side, you are observing the water level is very high. So if the gates of this dam are opened to certain extent, okay, means the hole is created here, then what we are observing, the water start falling and then this start moving this way. So here the water is stored. So in this dam we are observing that it is the stored water at very high level. So it is the high level of water. So wherever the level is high, it means what? Which kind of energy it has? The ground level is this one, a student, you have to observe. This is our reference level. Means from the ground, you are observing that the river, this is our river. River is always near or just on the ground, but the water on the other side of reservoir is at certain height. So because of this height, the water also have some mass. If we consider the upper layer of the water in this reservoir, this have which kind of energy? Potential energy.
Potential energy.
But when it is allowed to flow through the opening, when it starts coming down, it gains which kind of energy? Kinetic energy. So this way we are observing that the potential energy gets converted into the kinetic energy on the dam. And on the other side of dam, there is a turbine. This you will learn in next year. So if it is allowed to fall over the turbine, then over the turbine blade, the blade starts rotating and the generator starts moving. How is the figure? We will learn next year. So while rotating, blade is able to rotate the generator and electricity is produced. Okay. So this way, even potential energy of stored water converted into kinetic energy, that is converted into the rotational energy of the generator. This way electricity is produced finally in hydropower plant. So write these points. So in dam, so stored water have which kind of energy? Potential energy.
Potential energy.
And when the water is allowed to flow on the other side, then it gains kinetic energy. And water flowing on other side or in a river, this have kinetic energy. So what is happening on the dam? On one side, the potential energy gets converted into this kinetic energy. So while converting into kinetic energy, a generator is placed in the flow of this water. So while this water is falling on the blade or rotor part of this generator, it produces electricity. So right, this flowing water, this is allowed to fall on. So this is allowed to pass through the generator, the blade of the generator, not through the coil. Okay, student? So it is the blade of the generator or rotor part. So blade of the generator, basically one separate unit is there, that is called as the turbine. Allowed to pass through turbine. Turbine means rotating part connected to a generator. Turbine connected to generator the electricity is produced. Electricity is produced. Okay, this way we are observing potential energy into kinetic energy. Kinetic energy means the rotation into electrical energy. Where this is occurring, this potential and kinetic both are the mechanical. So this can be written as mechanical. Means within the mechanical there is a transformation from the potential to kinetic energy, then this mechanical to electrical. This is happening in our generator or turbine generator. Turbine is one part where this rotation is obtained, and the generation of electricity is occurring in generator, sometimes collectively called as TG, turbine generator system. More detail we will learn in class 10th. We have to learn there what are the colors. So here we have observed that one form of energy gets converted into the other form. Now the other simple thing, the third example. Now we can observe that in a swimming pendulum, what is this pendulum? Any mass, take just a ball or heavy ball, you attach it with an string or say flexible thread. Getting? So this heavy portion or mass is called as bob. This is your thread or string. If you are holding, keep it hanging, that will act as pendulum, or you may hang it from the ceiling. Ready? So this is the denotation of ceiling or the roof where you are just hanging it. It is hanging pendulum. A student, for this pendulum, say if it is just hanging like this, nothing is happening, then which kind of energy it have? A student, this bob, we are considering it at this level itself where it is hanging. Means this we are considering our reference level. Say this bob is just touching the ground or just touching your table or maybe hanging from the ceiling itself. This we are taking the reference level. So if any object at the reference level, then its potential energy is always considered as 0. That we have learned. An object laying on the ground, what is its potential energy? 0. Ground is taken as the reference level. Now, if I am pulling this bob on one side, means what? Now I am going to pull this, means hold it and try to, this end is the fix, where it will go? It will move over a circular arc or circular path so that this length remains the same. Are you getting? It becomes like this. So here we can observe that this, at this new position, what you are observing, at this new position, the bob have raised to certain height. This is the new height the pendulum or the bob of the pendulum have gained. So this new height h, because of this height, this bob or the pendulum will gain which kind of energy? Potential energy, student. So the center level, this level is called as mean position. mean position. If you have stretched on one of this side, this is called as the extreme position. Extreme position. Here you are just holding it. Okay, it was like this, you have pulled it aside and you are just holding. Okay, it is like this. Now, while it is on one of the extreme position, at this extreme position, this pendulum have which kind of energy? So it have
Potential energy.
good potential energy. Since you are holding, is there any kinetic energy? No kinetic energy, student. Why? You are just holding. Since v is equals to 0, so you do not have any speed. Now while you are releasing it, it will try to move downward, but because of the thread, it will follow the circular path. Like you are rotating anything, you are observing the rotating thing always follows circular path. So it will start following the same path and it will come down. While coming down, will it stop here itself? No, because of its tendency of motion or inertia of motion, this bob will continue to move on the other side. How long on the other side? You will observe that at the same height it can raise, as we have learned in Newton's laws of motion. There we had observed that because of inertia, the body will try to attain the same state. So because of that, it will come on the other end. So this is the other extreme position. Means this is the extreme position 2. So there will be two extreme position 1 and position 2, and one mean position. Again, while the body reaches to other end, you will observe here it momentarily come to rest, then it changes direction to come back. Because for turning the direction, the body must have to come momentarily into rest so that it can retrace its path. Like we are observing for a ball thrown upward, at the top of its journey it came to rest, then it turned its direction. In the same way, here also, even at the other extreme, and the speed is 0, means no kinetic energy. Or here the kinetic energy is your 0. But what is the potential energy, student? It have some height at same height. So have the potential energy, and that potential energy can be calculated also. If you have the mass of this bob as m, then whatever the m multiplied with g, and whatever the height from the mean position or reference level, that will be the mgh. The same potential energy here, mgh, on the left end. Means in this case, kinetic energy is your 0. So questions are asked at the extreme end of a pendulum. What is the potential energy? It is mgh. What is the kinetic energy? It is 0. What is the total energy, student, here?
mgh plus 0.
Total energy is still mgh only. Okay. So on this extreme end, the total energy is adding this potential energy plus kinetic energy. You will observe that the kinetic energy is 0. So only it is mgh. Even on this right extreme or at the extreme position 2, the total energy is again your sum of potential energy and kinetic energy. Means the kinetic energy
is equal to mgh.
Kinetic energy is 0. So again it is mgh. Okay. Now coming to mean position. A student, while the ball is crossing the mean position, means the lowest level, then you want to stop it, you will always get heated. Why? Because the body have speed at this mean position. You have left the ball from one of the extreme position, but while reaching the mean position, it gain speed. So at this mean position, so bob or pendulum mean the same thing, have speed. So because of this speed may be denoted as V. This implies it have kinetic energy, and kinetic energy is how much? That will be half
half
mass
mv square.
mv square. Okay, student, it is like this one. It is this much kinetic energy, but no height,
So
no
zero potential energy.
potential energy is your zero. Getting a student? It is like this one. We have to keep in mind from the extreme end, one of the extreme ends, say at the position 1, the bob is released or the pendulum is released. Released means the pendulum is stretched on one side, then it is released, allowed to swim downward. So while it is swimming at the bottom, you will observe it always have some speed v, but at their extreme there will not be any speed. Okay, so at this end the speed is zero, therefore its kinetic energy is zero. Okay, so these are the things that we have to keep in mind. Now if we calculate the total energy at mean position, total energy at this
Half
mean
mv square.
position or central position, it will be potential energy plus kinetic energy, but here the potential energy is zero, so it is only kinetic energy mv square. Is it okay, student? Now according to law of conservation of energy, if we just consider only one part, say the total energy whatever you are considering at extreme position 1 will be equal to the total energy at their mean position, this will also be equal to the total energy at their extreme position 2. So law of conservation of energy simply tells that, so by the law of conservation of energy or law of transformation of energy, the total energy at extreme means one of the extreme that you have to consider. You may consider at the extreme 1, or you may consider at the other extreme. So only one extreme that you can consider, 1 or 2, will be equal to total energy at their mean position. Mean position means the central position. Okay, it means what? This mgh should be equal to half mv square. Okay, means this can be equated. A student, here we are observing mm is common, so what it become? 2gh is equals to v square. Or what is this indicating? Here we are observing at the extreme position the u was 0. So this is in concurrence with, all right, like first this v square is equals to 2gh. So this can be written as 0 plus 2gh. So this is identical to u square plus 2gh when u is equals to 0. Means the kinetic equation is followed for this law of conservation. It means law of conservation is holding good. It is true. Getting? So this way, here the velocity can be directly calculated by taking the under root of 2gh. So two things we have concluded. One is kinematic equation, kinematic equation, or third kinematic equation is holding good, as we have learned in our chapter 1. Another thing, for calculating this velocity, I can just equate their energy at two states. Their velocity and height can be calculated. So this is the relation between velocity and height. Even for a body, when it is released from certain height, consider a body which is released from certain height h from the ground, means its u is equals to 0. Then with what speed it will hit the ground, student? Can you calculate for this body? We always have the acceleration due to gravity g. So since the speed v square is equals to u square plus 2as, that is the formula applicable. So here v square is equals to 0 square plus 2, acceleration is g since the body moving downward, and s is like our h. So whether I am applying the kinetic equation for calculating this, v square is equals to 2gh, or v is under root of 2gh, or we apply the law of conservation of energy, we are getting the same relation. It means this law of conservation of energy in pendulum is holding good. When the body is dropped by height h, the potential energy is reduced and it gets converted into the kinetic energy. So write that point here. So when pendulum moves downward, from its extreme position, from its extreme means end position, it's what is going to change? Which energy it is loses? Which energy decreases? Its potential energy decreases. And why the potential energy decreases? Because of the height, it is coming downward. And the kinetic energy, what about kinetic energy, whether increases or decreases? Increases, a student. Why? Since the body gains speed, when a body is allowed to move downward or even horizontally but with decreasing height, then its speed increases, so it gains speed. But always this sum of potential energy and kinetic energy is equal. Yes. So when pendulum moves downward from its extreme, its potential energy decreases and kinetic energy increases. It is point number 1. They're at extreme means end. Their potential energy is maximum and kinetic energy is 0. Even this potential energy can be calculated by knowing the mass of the bulb, g, and height from the mean position. You are getting now the mean position that we are taking, it is our reference. So this height we had considered, it is important.
Yes, sir.
So at extreme, at mean position, mean or also called as center position, what is happening? Potential energy becomes 0. Why? Since h becomes 0, but kinetic energy is equals to half mva square, half mva square, where this v is equal to 2gh. By equating these two, we are getting this. So these are the things that we have to keep in mind regarding the pendulum. So always for the moving pendulum, their total energy always remains constant. So that we shall keep in mind. When pendulum moves downward from its extreme position, its potential energy decreases and kinetic energy increases. But add just a small top. But total energy always remains the same. Remains the same. It is this. Means the total energy can always be equated. It's that way. Now let us go for writing the mathematical form of this law of conservation of energy. Student, here we have law. We have taken 3 examples to understand what is this law of conservation of energy. Law of conservation of energy simply means the total energy remains the same. Means if the body have one form of energy and the body is taking a new state, there the other form will be there. For the fan, while electricity is supplied, mechanical energy is produced. In the dam, the stored water have potential energy, but while it starts flowing, it gains kinetic energy and even electricity can be produced. For the bob or pendulum, on extreme only potential, but at the mean only kinetic, but the total energy always remains the same. A student, so mathematical form of law of conservation of energy. Students, we have learned according to law of conservation of energy what we have. Just I had written there. So this law of conservation of energy tells that energy can neither be created nor be destroyed, but its form can be changed. How the form changes? Means initially in one form, finally in some other form. For this, we are going to write for mechanical energy only. Though it holds good for heat and electricity also, but there the energy is expressed in different form. Like in heat, it is given by ms delta T, that we will learn later. In light, it is given by h into nu. H is Planck's constant, nu is frequency. So those things are not required at your level. So this law of conservation of energy for mechanical energy, though it is applicable for all kind of energy, but we are writing this equation for the mechanical energy. Here we have observed, say the pendulum have one state at one of the extreme and have another state at their mean position. So according to law of conservation of energy, the total energy of the body always remains constant. It simply means that always remains constant. Means what? The total energy is a fixed or mathematically written as constant. How is this total energy? Total energy is obtained by considering the potential energy plus kinetic
kinetic energy.
Yes. So that is our constant. A student, the potential energy mostly in gravitational field is given by mgh, and the kinetic energy is given by mva square. Good. This is constant. It's simply. So the law is like this one. But how to write this further, that we have learned about the law of conservation of momentum, where we were taking the two different states, and for that there are the different suffix and we can use it. Means if we consider a body is initially at height h, you may consider a body is flying. You may consider like that. Or say a ball is falling. You may consider, or a ball is thrown. Consider this ball is thrown, something like that. So you may consider for this throwing ball, I am considering the ball is moving over this path. So this is the ground. Finally, it is going to hit it here. I may consider the one state as this one. So this is the state 1 where the ball is thrown. Means at this time the ball has certain height. So for this state 1 or stage 1, it have the height h1, it have the speed v1. Therefore the ball is moving at certain height, it have the kinetic energy one kind, may be given as half m v1 square, and because of this the body have potential energy. So potential energy 1 mg and h1. Are we getting? So this way, because of the height, we can calculate the potential energy. One of the question that we have done regarding the flying birds at certain height, there we were calculating their potential energy as well as kinetic energy, then we were adding together to get the total energy. So here if we consider the two state, very first I have considered this one as the state or stage 1.
Stage 1.
Or sometimes stage 1 is also written, or a state 1 mean the same thing. Now we consider the same ball have reached somewhere here. Okay, still the ball is moving downward. At this time the speed will be different from this v1. It have the speed v2. Now what is the height at this time? Will it same as h1? No.
Decrease.
Difference height h2. So because of this v2, it have the kinetic energy given by ke2, means at the second stage as half m v2 square. And because of h2, it have the potential energy given by mg h2.
MgH2.
Very good. So it is like this one. A student, at this stage 2, what is the total energy as state 2?
Half
At this
MgV2 square plus MgH2.
Very good. At this stage 2, the total energy can be calculated by adding these two kind of energy. Yes, students. For getting the total energy, we need to add their kinetic energy as well as their potential energy. These two kind of energy. So write the total energy is equals to half m v2 square plus at this time mg h2. Similarly, at this stage 1, what is the total energy, student? Total
half mv
Half MV square plus MgH1.
Very good. So at state 1, it is given by half
mv
v1 square plus
mg
mgh1. Are you getting? Then according to this law of conservation of energy, then according to law of conservation of energy, we have whatever the total energy in stage 1, this much will also be equal to the total energy in stage 2. It's so simple. Getting? Means these two can be equated. That's why the total energy always remains constant. Is it okay? So, right? So, according to this law, the total energy in a stage or a state 2 will be same as total energy in a state 1. For the suffix 2, we shall write, for the suffix 2 we have written total energy is obtained by adding their kinetic energy. M, mass is same, mass is not going to disturb, but their speed have changed. So V2 square and their height have changed. G also remains unchanged because it is constant, 10 meter per second square, and H2 is equals to half M, initial was V1 square plus mg H1. Okay, so this is the relation, or this is the mathematical relation. So sometimes it can be written like this, or even this can also be arranged like this, or like this as half m v2 square. Bring this half m v1 square from the right hand side to the left hand side, and bring this mg h2 on right hand side. Mg h1 is already there, minus mg h1. What is this? This is the change in kinetic energy. It is the change in kinetic energy. They should be equal to the change in
potential energy.
Very good. So this way, whether you are stating this statement or this statement, both are the same thing. So you shall understand in MCQs, the statement may be given in the form of the total energy always remains constant, or may be stated as the change in potential energy equals to the change in kinetic energy. Both mean the same thing. Okay, student? So this way the questions are asked and they are very simple. Getting? So this you have to keep in mind. Therefore, we can finally write this as change in kinetic energy is also equals to change in potential energy. Sometime in this form, the question is also framed, though both represent the same thing. Okay. So it was all about our law of conservation of energy. Now one question is asked. We can prove that in a free falling body, the law of conservation of energy is holding good. So write that. So that energy is conserved. Energy is conserved means the total energy remains constant in a free falling body. Free falling body. Free falling body means, a student, a body is fall vertically under the influence of gravity. That we are going to prove. So here, let us consider a body of mass m is at certain height from the ground. This is the ground. The body is at certain height from the ground. Let us consider this height as h. Okay. Let us consider this position as A. Now the body is falling freely, means it will come down and it may reach to some other height. Let us consider at some height y. means this is the other height. We may consider this height as y. Then how much distance the body have moved or fall? Yes, student. How much distance the body have fallen? Initially it was at height h. Now the body have reached to position B, where is height from the ground is y. Means the same body A. Let a body of mass m fall, or let me write it downward. We can do some calculations here. Student, write this thing here. What the figure is representing? Let us write here. Let a body of mass m at height h, means initially the body is there, means this is the position. Which position in figure? A is falling freely. While falling freely, it have the acceleration due to gravity g and reaches to B. B is the intermediate position, then finally on the ground. Then finally on ground at C. So that this statement we are representing. The same body A reaches to position B. This position B, we are considering the body is at height y. Now when the body reaches to ground, once it will reach to this position, this is the position C. I'm writing this C here. A student, at A. So at A, what is the energy the body have? The body is released from height h. Means at this time we are considering its speed is 0. It means what is the kinetic energy of body? Kinetic energy at point A is 0. And what is its potential energy at point A?
mgh.
Good. The mass we are considering is m. It is always under the influence of gravity, so g, and height h. Therefore, what is the total energy at total energy TE is equals to kinetic energy at A, means this, let us consider the total energy at A plus potential energy at A. This is asked, student, it may be asked this year also. You have to write the examination there, this derivation will be asked. Means total energy at A will be what? You have to add the two. First kinetic energy is 0, but this is mgh, so total become mgh.
Yes.
Okay, student. So this thing we have to write for the position A. So write at A, body have no speed, so body is released. Released means the released from rest. U is equals to 0 or speed is 0. This implies kinetic energy is 0, but due to height, how much height is here? H. It have the potential energy mgh. Therefore, total energy at A, how much? This I have denoted TEA, total energy at A So kinetic energy at A plus potential energy at A. So adding this to 0 plus mgh, we are getting this value as mgh. Take this as equation 1. Are you getting? So at A, let us substitute the suffix A everywhere so that we can understand. So total energy at A we are observing is mgh. No kinetic energy. This even we have done here in rough work for explanation. Now coming to point B. While reaching to B, what has happened? The body, though it have initial speed u is equals to 0, but it gains some speed v. How much v will be there? This v can be calculated. So student, write here at B. So body have gain some speed, because while the body is released, it start falling downward, automatically its speed increases due to gravity. So body get speed due to falling downward, or due to gravity, or due to this g, acceleration due to gravity. Acceleration give rise to change in speed. So what is the speed at B? Initially, a student, just we shall understand this situation is like this one. The body is at A. Now the body have reached to point B. Here the u is 0, but at B we are considering the speed at VB. Okay, this we want to calculate. Now the body is under the influence of acceleration due to gravity g, and the body have moved a height downward. How much height the body have moved? H minus y, because y we have taken from the ground level, so the body must have fall by a distance of h minus y. So this h minus y distance is covered by the body. So body get speed due to gravity and falling down by how much height? Student, it is h minus y, where y is the distance from the ground, like h, y is the other distance from the ground. So therefore, not able to write, a student. So let me restart it quickly. So due to this h minus y, now by kinetic equation or kinematic equation, what is the relation? V square is equals to u square plus 2gh. This is the relation that we are knowing. Means 2as, better to write initially as 2as. In this relation, here we have the in this case the u is considered as 0 and the height covered is h. So s is as h. So this v is like our, the body have reached to at position B, so VB square, u is like this at A, means this is our 0 square plus twice the acceleration A is like our g, because the body is under gravity, and the height distance s is our height h here. So VB square is equals to how much? 2g, not this h but h minus y, student, because the body have fallen downward by h minus y. H minus Y, or VB can be calculated by under root of 2G H minus Y. This thing we have to keep in mind. So this we are observing that while the body have moved downward, at this time the speed of the body at B is under root of 2G H minus Y. Are we getting? So at B, the body have speed. This implies it have the kinetic energy at position B. It is given by half m VB. What is our VB? This much square means half m. But VB here we have calculated this as under root of 2G H minus Y. This is entirely under root. There is square. So the square root and a square will get cancelled. It becomes half of m into 2G, and H minus Y is in other bracket. Therefore, this 2 and 2 will also get cancelled. So this value will come as m, G, and H minus Y. It is important, student. So at B, the body have kinetic energy equal to mg H minus Y. It is interesting. But also, so this at B, the body is at distance or at height Y from the ground. This implies it have the potential energy at B. How much is the potential energy? That is given by mg, and height from the ground is Y. It is like this one. So this is the potential energy at B. Now what will be the total energy at B? Addition of these two, students. So just do it. Total energy at B is obtained by adding these two. Means one is kinetic energy at B and another one is potential energy at B. So substitute the kinetic energy that we have calculated, mg H minus Y, and potential energy is our mgy. Just solve it. Open this first bracket. It is the two term. So it is like our mgh minus mgy plus another one is mgy. Student, here we are getting that mgy and mgy are getting cancelled. The total energy is still mgh. It's very interesting. Okay. So this thing we have to write at for B also. Therefore, the kinetic energy at B is half m VB square. This calculation you have to do in down as I am writing. So just substitute this. Half m V square is our this much 2G, or under root as we have done there, 2G H minus Y. Simplifying this, we are getting this much square. This square and root are getting cancelled. Half m and then 2G H minus Y is there. This half of getting cancelled. It is like our mg H minus Y. Even these two can be separated. mgh minus mgy. It is the kinetic energy at B we have calculated. But what is the potential energy at B, student? That we have to write. At this B, the body is at height of Y. So at B, body at height Y from ground. Therefore, potential energy at B can be calculated by taking mg, and the height is now Y, so Y. Therefore, what is the total energy at B? Is kinetic energy at B plus potential energy at B. So this is equals to, substitute these two. Earlier we have calculated mgh minus mg Y was there. This was the kinetic energy at B, and potential energy, just it is written here. It is plus mgy. Here we are observing that mgy and mgy are getting cancelled. So it is our mgh. A student, what is the total energy at B? It is our mgy. What was the total energy at A? That was also mgh, and total energy at B is also mgh. The mgy was get cancelled. This also indicate one thing, the mgy, that is the energy or potential energy lost, is equals to this much kinetic energy gain. That is the other conclusion. Same thing we have to do for at C, means at the ground. A student, this is the last part of this derivation, so understand this. Now coming to point C. So at this time, what is the speed of this body at C? Observe, the body have started from u is equals to 0 and moved a distance or height h. So this is obtained by taking how much? U, h, g, that we have to calculate. And at this time, means at the point C, what is the height? Height is 0. So what is the potential energy at C when the body reaches to ground? It is mg into 0. So it is 0. But what is this? This we will do. Then we will calculate the kinetic energy at C. These two things first let us calculate. Let me calculate it on the other side. So student, at this C, observe the figure once again. The body was initially at height h when its speed was 0. It reaches to ground at the position C. This was A and this is our C. So what is this speed? A student, the body is under the acceleration due to gravity G. So in this case, VC square is equals to initially U at A, that square, plus 2G and the height h, or 2AS basically we can write. It is like our VC square is equals to initially the body released from A. So at A the speed is 0 plus twice the acceleration is G. The height for this point A is our h. So here we have to take this h carefully. Okay students, so substitute this h. So VC square is equals to 2GH, or VC can be calculated by 2GH. So here we are observing it have the value 2GH. So because of this VC, kinetic energy at C can be calculated. How much is that? Half m VC square. It is calculated by taking half m, and our VC is under root of 2GH, this much square. This square and this root getting cancelled, it become half, m is outside the bracket, 2G and h is there. Student, this 2 and this 2 will get cancelled, so it become like our mgh. What we are getting? The kinetic energy at C is mgh. Also at C, body at where? Ground. So this implies what is their height? H for the body or
0.
height is 0. This implies at C potential energy is how much? mg into 0. This is 0. Therefore, yes, what is the total energy at C, student? Add these two, kinetic energy at C plus potential energy at C. Kinetic energy at C we have calculated with the help of calculating the VC first, and this is our mgh plus 0. What is this value? This is also mgh. Therefore, total energy at C is also mgh. Now students, we have to compare this. Consider this as the equation C. at B that we have calculated here as the equation B, and initially that we had calculated for the A, total energy at A, means here you are getting, it was this one, total energy at A. Consider this as, say this as equation A. So from ABC, what we are observing, the total energy at A is your mgh, the total energy at B is also your mgh, as C is how much, mgh. Therefore, what we are observing, thus from A, B and equation C, we get what we are getting. Total energy at A is equals to total energy at B is equals to total energy at C. Means the total energy always remains same throughout the journey of the body. Therefore, total energy always remains
constant.
yes, remains same or rather constant. And what is this? This was equal to mgh. Okay, now so total energy always remains same throughout, means whether we are considering the position A or position B or position C or even any more intermediate position we are taking, the total energy is always same throughout the journey and on reaching ground for a free falling body. This was the free falling body. So this way, the law of conservation of energy is applied, or the total energy remains conserved. Total energy remains the same. This statement itself is called as energy is conserved. Energy is conserved in a free falling body. Okay, it was this. So this way we have proved that the energy is conserved in a free falling body. Okay, it was only this much, it's enough. So this was the thing to be proved, and this way we had proven. Okay, means the total energy at A or B or C is always the same. The same thing in short we had written over this diagram itself. So here VC we have calculated is coming as 2gh under root, and kinetic energy is also coming as half m then under root of 2gh, whatever the calculation we had written, it is our mgh. And the considering this total energy at C we had calculated as the sum of potential energy and kinetic energy, means it was mgh plus 0, it is our mgh. So this way, over this figure I have explained also that the total energy at C is mgh, at B is mgh, at A is also mgh. Are we getting? So therefore the total energy always remains same. So it was this one. So this was all about this chapter, but a very small topic. Let us do it. What is called as the power. Power is very simple thing. So let us finish it today so that the chapter can be finished. Student, this derivation is very important. It is asked in your 4 marks. So let us go for the last topic called power, or also called as rate of doing work. A student, this power, the definition of power is that it is rate of just doing work. So it is rate of doing work, or doing work is called what? Energy. Okay, or either consuming energy or dissipating energy. Rate of doing work or energy used or energy produced, see, consumed, or maybe your energy produced also. A student, doing work is same as energy. That's why rather than only work, we can write in the term of energy also. That we have seen. For calculating the energy, we need to calculate the total work done. It was that one. Now, what is this rate? A student, rate simply means anything divided by time. So anything divided by time is called as rate. So if we consider the work done is W and this much work done is in time T, then the rate is obtained by dividing W by T, means in 1 second how much work is done, that is called as the rate. Okay, so this is sometimes also defined as it is work done in 1 second. Means work done per second or work done in 1 second, in 1 second, or maybe written as work done per second. It is this. A student, consider a body is there. A student, this body have moved to some other position. There might be some force F applied over this, so that the body is being displaced by distance of D. Therefore, in this case, from moving the position A to position B, the work can be calculated by F into D. Okay, it is one thing. But while moving from position A to position B, it might have taken some time. Okay, so at A, it was at the time t is equals to 0, and it was at the time t is equals to t. So at 12 o'clock it have started and it have reaches to B at 12:30. So time taken is the 30 minutes. So it is this t time taken. So after this, how much work done in 1 second? So here we are getting that in 30 minutes W work is done. So how to get the work done in 1 minute or 1 second? Total work by 30. It's so simple. So similarly, so to define this, we have to write like this. Let a body is doing work W in time T. Means in time T second the work is done. How the work is done and how it is achieved in real practice, it is drawn on in this figure. Means the body might have displaced certain distance by some force. So while doing this, the body might have taken some time. That time is T. And while during displacement, the work W is calculated by F into D. Okay. Then the power of this body or power is given by this work done divided by time taken, by its time in which this work is completed. It is this one. In symbol form, this power is denoted by P and W is denoted by W. means work is denoted by W by T. Okay, or this work done is sometimes also given as energy, so it may be the energy by time also. Because work done is same as energy, so power can also be defined as rate of doing energy also, E by T. So rate of doing work or rate of giving energy, that is called as the power. Students, so the definition of power is only this much. Now it is the very first definition, how much power is there, that can be calculated by knowing the work done, dividing it by W. Also, for a constant force, how much work is defined or how the work is defined, as we have drawn in this figure. How the work can be calculated? F into D. So work is calculated by F into D, force into displacement. Therefore, this power P can be calculated by substituting this F into D divided by time T. Can we do like this, students? Surely we can do. What we have done, we have substituted this W in place of the definition of power. Therefore, we have written F into D. Now, this can be rearranged like this. Take this F outside. What is this? D by T. A student, what is this D by T? D is our displacement. And what is this T? Is our time. A student, displacement by time is called what? This gives the velocity. Getting? So we can substitute in place of this D by T as velocity V. So this power can also be calculated by power is equals to force into its speed. It is rather the velocity or magnitude of velocity, that is better word. The or speed in only one direction. So velocity. Here the magnitude of velocity have to be taken. So this is the alternate formula for power. Now, student, what is the unit of power? How we can calculate the unit of power, student? So unit of power is equals to, substitute in this formula the definition of power. Unit of work by unit of time, it is this one. Therefore, what we can write, even we have to do here itself. So unit of work is what? Joule. And unit of time is what? Second. So this can be written as joule per second. And this joule per second is called as, this is called as watt. W-A-T-T. Therefore, 1 watt, WT I am denoting. Because to get a watt confusion with W, I am denoting by WT, is equals to 1 joule per second. It is the relation. So question is asked for defining the 1 watt. So what is this 1 watt, students?
Joule
1
per
watt
second.
is nothing but it is the work done. So define 1 watt. Just we have learned 1 watt is obtained by 1 joule per second in 1 second, or 1 joule per second in this form. Means 1 watt is 1 joule of work done in 1 second. Is what? 1 joule of work done in how many time? In 1 second.
1 second.
So you have to define these units in a simple manner. How it is obtained from the formula. It is this much simple. Okay, student. A student, here sometime we are taking this time into the hour also. So watt is a smaller unit, very smaller. It is denoted by W. Another bigger unit could be the kilowatt. So kilowatt is bigger unit, and this is denoted by, kilowatt is denoted by kW. Write this, kW is bigger unit. Like gram is the smaller unit and the kilogram is its bigger unit, kg. Then what is the relation between kg and gram? It is 1000 gram.
1000.
In the similar fashion, 1 kilowatt is nothing but it is 1000 watt. Okay, student, you have to keep this in mind. So watt and kilowatt are the unit of power. A student, there is another way of expressing the unit of energy in term of power. So let me write that one also. Unit of energy in term of power. Students, just we have learned the power can be defined as work done or energy by time. It's okay? Means the work or energy can be written as power into time. Just rearranging this. Means this formula that we have learned, the definition of power, multiply this power with the time, you are getting the energy or work, because energy and work are synonymous thing. Do not get confused. So this unit of, just a minute. So unit of this energy can be written in the term of unit of the power, because the power we can define in watt or kilowatt. Then the unit of energy can be expressed in the term of kilowatt also. So substitute the unit of power as kilowatt and time as hour. It is called as kilowatt hour. That is the other unit we are coming across most commonly while we are doing the billing, means the electrical billing. So students, write this. So when this power is expressed in kilowatt and this time is expressed in hour, then the unit of this means the unit of energy can be obtained by considering the unit of power in kilowatt multiplied by the unit of time in hour. So this unit is called as kilowatt hour. So write unit of energy can be, so this kilowatt denoted by kW and this hour by H. Therefore, the question is asked kWh, or many a time kWh is a small, or in full form kilowatt hour, it is a single term, is unit of, yes, kilowatt hour is the unit of power, energy, work, or distance, displacement, pressure. Whom unit is this kilowatt hour, student?
Energy.
Very good. So kilowatt hour is the unit of energy that you have to understand. And this is used in electrical billing or metering. You are paying your electrical bill, you are saying your electrical bill is 5 unit, means how much? It is 5 kilowatt hour, student. Are you getting? And used in electrical billing or energy meter. So whatever the meter for which you are paying the electricity bill, it is the measurement of energy that you have consumed, not the measurement of power. Okay, in house or industry, it is this one. So 1 unit, so this is called as used in electrical billing or in energy meter in house and industry, called as 1 unit or 1 electrical unit or 1 BOT unit. It is called board of trade, means how the unit is measured for electricity. So 1 unit of electricity means how much, student? Means it is 1 kilowatt hour. It simply means, so 1 unit is equals to 1 kilowatt hour. This you have to keep in mind. Now since this kilowatt hour is the unit of energy, this can be in term of joule also. So this kilowatt hour is equals to how much joule, that we have learned that the energy can be expressed in the term of joule. So this kilowatt hour can be expressed in the term of joule. So write that 1 kilowatt hour. For converting this into joule, recall that what was our watt? The definition of watt was joule per second. Means 1 watt was joule per second, or joule by second you may write. 1 watt as joule by second. So 1 watt into second is equals to 1 joule. So wherever watt into second comes, that can be written in the term of joule. It is one thing. So for getting this kilowatt hour in term of joule, I need to first convert in the term of watt and second. Then only we can write. So therefore, convert this in the term of kilowatt into what? 1 into 1000 of watt. Okay. For hour, 60 into 60 of second Is it okay, student?
Yes, yes,
Yes,
sir.
because this watt and second can be separated. So write this 6 into 6, 36. Then 2 0 and 3 0 are here. 2 and 3 more. This much watt into second. Now, a student, observe carefully. What is this watt into second? It is our joule. Here we have written. Since watt into second can be written as joule. So this can be written as 3, 6, 1, 2, 3, 4, 5 joule, or in the term of the exponent, this can be written as 3.6 into 10 to the power 6 of joule. Are we getting? So this is the relation. So we can write this 1 kilowatt hour as either 36, after that 50, or 3.6 into 10 to the power 6 joule. So we have to keep in mind 1 kilowatt hour is the unit of energy, and it is equals to 3.6 into 10 to the power 6 joule. It is very important relation. Questions are asked so many times. So we have to keep this thing in mind. Okay, student. So this was all about this chapter. Everything I have explained, considering everything. Okay. So we have to keep in mind this kilowatt hour is the unit of energy. Okay. And it is used in electrical billing, also called as simply 1 unit. So 1 unit simply means 1 kilowatt hour. So if you are given with say 72 kilowatt hour, then how much joule is that? You can convert it. Or how much unit is that? You can convert it. Those things we will do next day. Okay, student. So how the questions are asked, you please practice in your home. These things we will discuss even tomorrow. Then we will go for the new chapter. We will solve this numerical, but do not wait for that. For solving me, you can do it. Let me give some hint. See, a student, the question is like this, and we have to solve it. Here it is given that this is solved question from your book. Two girls, each of weight 40 Newton, means the girl A and B, they are. So A, its weight is, means the weight mg is given. Okay. So this is like our mg value. The value of mg is 400 Newton. And for the other B, the weight mg, this m into g, the product is given as 400 Newton. If only mass is given, then you have to multiply it with g. Even mass you can calculate by dividing it by 10. So 40 kg. If you want to get the mass of A, that is obtained by weight divided by g. So 400 divided by g value is 10. So it is 40 kg. So even you can calculate the mass here also, or directly you may use the value of mg here. So climb up through a rope of 8 meters. We name the girl A and B. The girl A takes 20 seconds. Now understand this. Both of them are climbing to a height of 8 meters. The girl A takes 20 seconds. The girl B, for climbing the same height, 8 meters, this girl B takes, TB is here 50 seconds. 50 seconds. It is our TA. Then how much is the power? So what is power of girl A and what is power of girl B. These two things are asked. A student, commonly we are knowing that what is this power? Power is given by work done per second. But while climbing, even last day we have also learned, while climbing or moving under the gravity, this work done is obtained by calculating their mass with acceleration due to gravity, and that multiplied by height, means the weight with the height. Weight is the force and height is the displacement. So work is obtained by mgh and time t. Or even yesterday we had also learned, while the body is climbing upward, it will gain the energy of mgh, mean the same thing. So here for the body A, we have to calculate mgh. This value is same because each of these have the same height. Even the height is different, then we can put the HA by TA. And for the body B, the power is obtained by mg, the same weight is there, HB by TB.
TB.
Yes, here we are getting HA and HB are the same.
Yes,
okay,
sir.
friend? And mg is also the same, it is 400 Newton. So substitute this mg entirely as 400 and HA as 8 divided by 40 TA.
20.
Here TA is our 20. So we have to substitute 20 here. But for the power of B, the mg value is 400 and
400.
height is now also 8.
8.
But the time in this case is how much?
50.
Are you getting? So it is the 50 that makes the difference. Now just cancel it. 0 to 0. Then 8 to 4. So it becomes 4 4s are 60. What is the unit? Unit is watt. But for the B, how much is this? Cancel this 0 to 0. And this 8.
8. 8 plus 64.
Yes, how much is this? 64 watt.
64 volt.
Volt, not watt. So here we are observing the power of A is 160 watt, but power of B is 64
Only
watt.
What?
Who have the more power? So those who are
PA.
taking lesser
PA.
time have more power. So power is inversely proportional to time. Means
Time.
lesser the time, more the power. Here, power of A is greater than power of B. Okay, this was all about this problem. Now let us come to the other question of 11.9. Students, here it is given in the term of kilowatt hour because it is electrical bulb of 60 watt. So note down the data. Electrical bulb of 16 watt. 16 watt is denoting what? The power of bulb. You may write like this. Power of bulb is 60 watt. Is used for 6 hours per day. The time is how much? Time is here 6 hours.
6 hours per day.
Good. So per day is equally important, a student. Okay, now? Now calculate the unit of energy consumed in 1 day by the bulb. So in 1 day, how much hour it is going to use?
6 hours.
6 hours. So a student, energy consumed, how we can obtain? This is power into time.
Power
But
into
for
time.
getting this into the unit, means the unit, for getting this into the unit, this power must be in kilowatt.
Kilowatt.
This would be in hour. This thing we have to keep in mind. Is it okay? But what is
Yes, sir.
given here? The power is given in the watt. So first convert it into
Power is given in watt.
kilowatt. How we can convert it into kilowatt? For that, the 60 have to be divided by
Divided by 1,000.
very good.
Multiplied.
No, divide it by 1,000 so that you will get into kilowatt. Because 1 kilowatt is equals to 1,000 watt. So 1 watt is equals to how much kilowatt? 1 by 1,000 of the watt. So 60 watt is equals to 60 into 1 by 1,000. So 60 by 1,000, it is like this one. So it becomes 0 to 0 can be cancelled. It becomes 0.06 kilowatt.
Into 6.
So it is this much kilowatt. A student, it become equal to 0.6
06
kilowatt.
kilowatt.
This is important. So I shall substitute. So energy in unit is equals to which value I shall substitute? Kilowatt. That we have calculated or converted here. Are we getting?
0.06.
Very good. So we shall not substitute the 60, rather we shall substitute 0.06. It is this one, this value. So be careful while we are using this unit term. So it is our 0.06. So only this value have to be taken while we are want to calculate in the term of unit. So it is like our 0.06. Now time in hour,
6
hours.
6 hour. But how many day is there? Into only 1 day. Because
1 day.
it is asked for 1 day. If there is 2 day, then you have to put here 2. Getting? The number of day you also need to multiply so that the day and day will get cancelled. Total working hour is obtained. So how much is this? It is our
0.36
0.36 kilowatt.
kilowatt.
You may
Hour.
write this as kilowatt hour or 0.36 unit only. It is the way. So you have to pay the bill for that. In this same question, it may be asked if cost of 1 unit is 3 rupees, then what will be the bill? Yes, can you tell me? What
0.36 into 3.
Very good. What will be the bill paid for the month? A student, here the question is slightly changed. So month in above question. Here now it is asking for a month. So what is the total unit consumed in a month? So this was in 1 day. So in a month of 30 days, so month are of the varying days. So let me write of 30 days. Month was there, or month of April or May may be there. From there you have to consider the number of days. So student, so the energy is calculated by power into time. So in this case, for the entire month, I shall take 0.06 into the 6 hour. In the month of 30 days, I shall need to multiply it by 30.
30.
So this much unit in a month. Because of this month, we have multiplied this 30. So how much it become? Multiply this. So it become, so 8, 2 3s are 8. Just multiply this 0.36. Yes, 108. So the one more 10 is there. So it is 10.8 unit. Is it okay? So this is the unit. But what is the cost? For the cost, you shall multiply this
10
by the rupees 3 for each unit. So cost is equals to total energy multiplied by the cost of each unit. Each unit means the bill paid. It is basically the bill that we want to calculate. Means the total bill is obtained by considering the two. So it is our 10.8 unit into rupees 3 per unit is here. So 3 more is there. So 24. So 3 2.4. So this much rupees is the final answer. So 32 rupees 4 paisa will be the bill for this month. For a month. So students, questions are framed based on considering their unit, their number of days, their working hour. So we have to take care. So this was the concept that we have to use. Now this way we have finished this chapter. Now your duty to do the blue question on the page number, where is that? The page number 56 and the exercise question on page number 56 plus exercise questions. All question you please try, then you ask tomorrow. Tomorrow we will discuss if you have any doubt. Otherwise, if you do not have any doubt, then we will continue or we will go for a next chapter that we will decide later.
Sir, math.
Yeah. Yeah, student, which chapter we shall start? Whether maths or one chapter of biology or what we shall do? Yeah, you please tell me. We shall continue with the